Continuing with this series of videos, sort of doing some inspecting and critiquing, maybe, of how conventional physics is taught and what concepts are promoted in physics, generally speaking, as presented by Professor Lewin. Such. So we're on LRC circuits and metal detectors.
With these rather simple equations, they're really not that difficult. Here, this is really the heart of the equation, and then of course your tangent phi, in case you're interested in the phase legs. But they're really not that difficult. I will not hold you responsible for being able to derive the solution. I give you the solution, but with that solution you can do a lot, and you can understand the behavior of these circuits quite well. Now I'm going to do a demonstration, and I warn you, you have to follow very closely, step by step, what I'm going to do. Because if you miss one small step, you're lost for the next 12 minutes. Completely lost. You'll just see nice things, but you don't know what you're looking at. So follow me closely.
Yes, so for a staged experiment, no doubt, but whatever, we'll see if we can find some way to reason around it.
I have an LRC circuit, and the LRC circuit is right here. This is my L, 0.1 Henry. These are my C's, and this is my R. It's a 200 watt light bulb. I have an LRC circuit, and I will give you the values for L, for R, and for C. I'm going to drive it at 60 hertz. So omega equals 377 radians per second. And whatever you're going to see for the next 12 minutes, that is not going to change. That frequency is a given. I simply plug it into the wall, and so my driving voltage is 110 times the square root of 2 times the cosine of omega t, and it is this omega. So it's the 110 volts that comes out of the wall, so to speak. My light bulb R.
Let's just understand that this, divided times the square root of 2 is, essentially times 1. So it's just, it's just add-ons that you don't really need. You don't need to be that specific to get the principle involved.
Is 60 ohms when it is hot, and it is a 200 watt bulb. So if it's bright, 200 watt bulb. The self-inductance L is 0.1 Henry, and the capacitance is 8 microfarads. So this is God-given. With these three values, I can calculate what Z is, and Z is 300 ohms. In case you're interested, I can also give you omega L, that is 38 ohms, and I can give you 1 over omega C, that is 332 ohms. So notice that this is by far the dominant player in the game compared to omega L. In case you're interested in the resonance frequency, omega 0 is 1 over the square root of LC, and that is about 1120 radians per second. In other words, my driver is nowhere near resonance. I am way below resonance. When you're way below resonance, it is the C that dominates. Look at the 332 ohms and compare that with the 38. I can calculate now what the maximum current is that we get, I max. That is V0 divided by Z, that impedance. So that is 110 square root 2 divided by 300 ohms, and that is 0.5 amperes. And now I can tell you how much power is dissipated in the light bulb, which is I square R. So in the light bulb, which is the only component which has a resistance, well, maybe the L has also a little bit of resistance, but we will ignore that for now. So in the light bulb, the average power over one full cycle of my oscillations equals the mean value.
I would assume, since it's only 0.5 amps, you've already sort of dictated what the wattage is going to be, and the wattage is all going to be dissipated through the light bulb. So it's just going to be 0.05 times that, which is 1/4 of the bulb's capacity, which would end up being somewhere around, 50 watts.
Between I squared R, time averaged, the time average value of cosine omega t squared is always 1/2. So this 1/2 that comes here is the result of the fact that the I there has a cosine omega t, and you square that, and you get 1/2 if you average it over oscillations. And so now I get I max squared times R. So this is 1/2 times my 0.5 squared. And the R of the light bulb is 60, and this turns out to be 7.5 watts. Nothing.
Well, pretty low for 0.5 amps. So again, I don't understand how you can throw 5 amps into half an amp and get that low a result, but whatever.
Why is it nothing? Well, that's the way we designed the system. We're way below resonance. So if I plug the system in, which I will do for you, this 200 watt light bulb will only dissipate 7.5 watts, and you won't see anything. You ready for this? 3, 2, 1, 0. Physics works. You see nothing. Light bulb not working. Great. So now
So the real point would be is that the 0.5 watts was at some different circumstance because there's nothing else to suck up all that energy.
the question, what could we do to get the system back on resonance? Well, we know that our driving frequency is 377 radians per second. And so
So again, why change these things? You got a wavelength, you got period, you got frequency. Instead, now we're going to use radians per second. Just no point in making it more complicated.
what we could do, we could change the C in the circuit, and we could change L in the circuit. If we increase C or we increase L, then the resonance frequency will shift from 1120 down, make L larger or make C larger, then obviously you shift your resonance frequency down. And my goal is to shift it down to 377 radians per second. I first want to make a curve for you here, very roughly, of I max as a function of frequency, omega. And that's the demonstration I just did. When this was 1120, we had about 0.5 amperes at our value of 377. So this is one point of our I max versus omega curve. I can now ask the question, if we drive the system at resonance, what then would have been the maximum current? We're not driving it at resonance, but suppose we had driven it at resonance. Well, at resonance, I max is V0 divided by R. There is no self-inductor, and there is no capacitance at resonance. And so that would then be 110 square root of 2 divided by 60. But that is 2.6 amperes. That is substantially larger than 1/2. So this value here is 2.6 amperes.
Yeah, right. So you just multiply the amperes times the voltage, and that'll give you the wattage. Which,
It is too bad that I can't go there, because I am stuck to my 377, and I'm not going to change that. Throughout the demonstration, I stick to my driver here. So keep in mind that the driver is always here. Don't change that. So the resonance curve, we call this the resonance curve, is very broad, something like this, and I believe the Q is around 2. You can check that for yourself. I can calculate what the power is that the bulb is dissipating at resonance. Well, that is my 1/2, which is the time average cosine squared. My I max is now 2.6 amperes, so now I get 2.6 squared, and my resistance is still 60 ohms. And this is 200 watts. What a coincidence. That's the way we designed the experiment. So if we could be at resonance, the light bulb would be happy like a clam at high tide. It's exactly 200 watts. It wants 2.6 amperes. That's what it wants. That is a 200 watt light bulb. And so we want to make the light bulb happy. And how can we do that? Well, we can either increase L or we can increase C. And I want to catch 2 birds with 1 stone during this demonstration. I'm going to teach you a way that you can increase L, something that we have never discussed before. I have
he'll stick a core in it, I think.
here ferromagnetic material which has a value for kappa somewhere around 10, 12. Let's say it is 10 for now. So that means that if I bring that iron core inside, that I could make this go up to 1 Henry. Because remember, the meaning of self-inductance is the flux divided by the current in the solenoid. And so if you bring in ferromagnetic material with a kappa m of 10, then the flux goes up by a factor of 10. The current remains the same, and therefore your self-inductance goes up by a factor of 10. So you see that you can make a variable self-inductance by bringing in ferromagnetic material and by removing it again. And so the question now is, how high should L be to get on resonance? Well, that's very easy, because we know that 1 over the square root of LC, we want to make that 370, that's our driver. But we know that C is 8 microfarads, that's a God-given, we're not going to change that. And so you can easily show now that if only we could make L 0.88 Henry, we should be back on resonance. Then we have 377 radians per second as our resonance. And you shouldn't be surprised that omega L is then 332 ohms. Of course it is 332 ohms, because it's going to eat up that 1 over omega C. They're going to cancel each other. That's another way that you could have calculated the value of L, by simply saying omega L has to be 332. So there are various ways to get your resonance frequency. And so what I have done, if I make L 0.88 Henry, I shift the resonance frequency to this value, and the resonance curve now will look like this. So this height is going to be the same, because the height is only determined by V0 and R. And so what I'm going to do now is I'm going to turn on the instrument where it was before. But this was the resonance curve. You won't see any light. And I'm going to move the bar in. I probably don't have to move it in all the way. And then the light bulb will go through resonance. The system will go through resonance. You will get your 2.6 amperes, and the light bulb will be happy.
The 88 number he had down there before, sort of 88.88 Henry, when 1 Henry gave you resonance. So, seems like he has to push it in 88%.
So let's do that now. All right, so here, system is now, current is going. 60 hertz, 110 volts, root mean square as we call that, and it's way off resonance, 7.5 watts, the light bulb doesn't even feel warm. Now I bring this enormous piece of iron in there, and when I shove it in, the self-inductance will slowly go up, the resonance frequency will shift, and the current to the system will increase. And there we go. There it is. I'm on resonance now. So the light bulb is quite happy. I want to do one more thing. I'm going to double the capacitance. And what happens when I double the capacitance? The frequency, the resonance frequency, goes further down than it was already. Because remember, when you increase L or C, the resonance frequency goes down. So I'm going to double the capacitance. So that curve that you see on the left there has shifted now even further to the left. And the light bulb is not very happy. The light bulb is, the system is off resonance again.
You gotta pull it.
If I increase C, I double it, I can decrease L by a factor of 2. All I have to do is pull the iron slowly out. And then the resonance frequency comes back at 377 radians per second. Watch it. Back on resonance. Amazing, isn't it? Physics works. So, I showed you this demonstration and I spent so much time on it because...
Not exactly amazing, but whatever.
I want you to appreciate, want you to be able to see through these equations. The answer in physics in general lies in the equations, but it only works if you build up a certain amount of understanding. And that is not always easy in the demonstration.
I just point out that the equations are a little bit more convoluted than they need to be. And that I'll just point that out. And the 1/2 times something squared, it's obviously taking an average of the thing being squared. So, sometimes, the higher the number goes, the more that doesn't mean much. But obviously, that's not a complex idea. Let's just say it that way.
Help that. Seeing is believing. And you may have to go over this at home in order to digest it a little bit. I don't expect you to get all this just in one lecture. Of course not. We have a new impedance here, we have the reactance here, we have the idea that omega L eats up omega C, and we get into resonance. All these phenomena take time to digest. There are many key practical applications in LRC circuits, more than you may think. Your radio and your TV are systems that you, without realizing it, you tune them to resonance.
Yeah, so it's that old tuning thing, discovering radio waves. And it's a key point to make is that this energy isn't something you can just detect, you know, without filtering it out of all the other stuff that's coming in. So, you know, that's what makes it, I mean, it's kind of obvious our eyes are able to do that, picking out light. But these are just ways of filtering for frequency. And that's something you have to do to detect a lot of energy, is to filter it out of all the noise that's in the environment. Yeah, what else can be said about that? And so there's a certain flaw, I would argue, in some experiments because they are frequency dependent and you have to be able to tune to them. And if you can't tune them, you can't see them.
There's an antenna that receives many, many stations at all different frequencies, and you're changing, in general, you change the capacitor. And when you change the capacitor in the LRC circuit, you are changing the resonance frequency, and at that resonance frequency, the system is very sensitive, drives a very high current, and it selects then a particular station at that frequency. That's what you're doing with your TV, and that's what you're doing with your radio. You're changing a variable capacitor. Another application, which is quite common, are metal detectors. Metal detectors are resonance circuits. They are set at resonance.
So they're sort of like the iron bar inside the solenoid. So what's happening is you have a coil, and you put iron, not in the coil, but near the coil, and even that's enough to increase the flux inside the coil and you know, change how much energy it's trapping, and that changes the resistance.
And then when you bring metal nearby, you move them off resonance, and then the alarm goes. In general, they have two coils. This is one coil, and this is another coil. Inductance L1, resistor R1, capacitance C1, L2, R2, C2. So there's a current I1 running through this one, the current I2 running through that one. To set up the differential equations for this system is not so easy. You get two differential equations, of course, one for this system and one for this system. The problem, but at the same time the trick, is that there is a mutual inductance between the two, because when this one produces a current I2, there is a magnetic flux going through this one. That's why we call it mutual inductance, which we have never really dealt with in any detail in 802, and we won't. But I want to mention that this differential equation here is an equation in I1, L1, R1, C1, but also contains a term m times di2 dt. And this differential equation is an equation in L2, R2, C2, I2, but also contains a term m times di1 dt. And so now you get two coupled differential equations. It's not just one in I1 and one in I2. It is one in I1 and I2, and it is another one in I1 and I2. And that is a pain in the neck, and it's not easy to solve. But there are mathematicians who can do all that, and they solve that for us physicists. In any case, what is important to know that clearly, since you have two coils, you get two resonance frequencies, not just one, but you have two resonance frequencies. And at least one of those resonance frequencies depends very strongly on the mutual inductance. And so the system is tuned to set at one of these two resonance frequencies. And now someone brings in metal. You bring in a chunk of metal. And in this metal, the metal will experience the magnetic field flux changes, AC of course always. In the metal it will start building up eddy currents. And so the eddy currents will change the magnetic coupling between these two loops. And so M changes. And when M changes, you go off resonance, and bingo, your alarm goes off. Clearly, and very unfortunately, this never works for plastic bombs. You must have conducting material that you bring in, so it must be a metal. These systems have very high Q. Very high Q means they're extremely sensitive. If you have very high Q, that curve is extremely narrow, and so the slightest change in M, you go off resonance, and you get your alarm. And so they come in various forms and in various applications. At the airport, it is very simple. You walk through these two coils. You may not have realized that, but you simply walk through. You walk through like this, one coil here, one coil there, and that's how they detect whether you have any metal on you. The metal detector
makes it easier that way is the point. So the closer you can get metal to the coils, obviously the better, to in between them, but obviously you can't do that in the ground.
That I use to search your body, including the ones that I used to search the ground for coins. And when I was a kid, I went often to the beach in the Netherlands, and there were often people who were having these metal detectors. They were looking for coins. And those metal detectors are basically the same idea. Always two coils. This is this coil, and this is this coil. And when metal comes nearby, you have a system that goes off resonance. You get a different magnetic coupling.
I guess it's sort of like a transformer, except you're charging both sides, and but the secondary and the primary are communicating, and any metal will change their communication
Between the two coils, and the system goes into alarm. And I'd like to demonstrate that, for which I need a student. Any student who wants to volunteer, I have here a metal detector. And thank goodness we don't have to go through metal detectors yet at MIT. You want to volunteer? Boy, you're brave. You're all the way to the end of the... Can't wait what you have in store for us. Well, you look like you're made of steel.
Look like a...
Okay.
I don't even know what to say it looks like. Politically incorrect to say what it looks like.
I hope you left all your secret weapons up there, did you? So this is a metal detector, and if you open this up here, you would see two coils, one in the center and one near the edge. And so I have to calibrate it first. Okay. Oh, you left your cigarettes out there? They won't record. What did you leave out there? I'm just getting curious. Oh, you're afraid that it will get damaged? Oh, we hear nothing. That's nice. No, that's probably not working. Well, just a second. May have to recalibrate this. Pretty quiet. Doesn't look like you have any metal there.
Probably just have batteries in it or something.
I'm fairly sure I turned it on. They don't always work, do they? Marcos, you have any wisdom on that? It's working. No, it's not working very well. It's working well here. I wonder what you got there. Are you metal? Is this not made of metal, all these things here? Well, you may be a weird person. That is...
There is a setting on metal detectors for the ferromagnetic versus the paramagnetic. So he probably has it set to the steel setting.
Can you turn around? Get your watch. You better turn around again. Ah, there are the keys. You're not made of steel, but you're a great guy. Thank you very much. Today is Wednesday, right? See you Friday.
Well, not a lot to work with there, but whatever. And I didn't do much with it. There was little offered, and I did little with it. So sorry about that. Just the concept again is that the metal creates an environment where it can start to reflect the energy thrown at it. And that's really all this is about. And once it starts reflecting, the reflections magnify and blah, blah, blah. And in terms of the capacitor and an inductor, they're basically just, complementary to each other in the sense that they can be in or out of sync in the sense they both require charging. So if you're putting an alternating current through them, they have switching over times. And when they're not in sync in terms of their switching over times, then they're going to waste a lot of time pulling against each other rather than working with each other. So the idea is to have them both charging and discharging at the same time, and then they'll go with the flow better, and you'll be able to push more current through them. Something like that. Anyway, until the next time, and such.